Hey everyone, welcome back. Today, we are diving deep into a really powerful algorithm called heavy light decomposition, or HLD for short. If you've ever found yourself staring at a tricky tree problem, wondering how to make it faster, well, this is one you're going to want to know. So, picture this. You've got this gigantic tree, maybe millions of nodes, and you need to answer questions about the path between any two nodes. Questions like, what's the sum of all the values on this path? Or what's the biggest number on that path? And you have to answer thousands of these queries, fast, like almost instantly. How on earth do you do that? Well, that's the core of what we call the tree path problem. If you try to just walk the path for every single query, your program is going to be way too slow. We need a much smarter approach. Yeah, the obvious way, the brute force way, is a total non-starter. If the tree is deep, traversing that path every time just doesn't scale. The whole game is about doing some clever work up front, pre-processing the tree, so that later our queries are lightning fast. And that brings us to the central idea behind heavy light decomposition. We're going to break the tree down in this really specific and honestly kind of brilliant way, using two key concepts, heavy paths and light edges. Okay, so first up, what in the world is a heavy edge? For any node in the tree, just look down at all its immediate children. One of those children is special. It's the one that has the biggest family tree, the most descendants. The edge that connects the parent to that specific heavyweight child, that's our heavy edge. It's all about subtree size. And if an edge isn't heavy, well, you guessed it, it's a light edge. These are the edges connecting a parent to all its other smaller subtree children. This simple little distinction, heavy versus light, is the foundation for everything that follows. It's what makes the whole algorithm work. And this right here, this is the secret sauce. This is the magic. Think about it. If the heavy child has the largest subtree, that means any light child must have a subtree that's, at most, half the size of its parents. So every single time we travel up a path and cross a light edge, the size of the subtree we're in gets cut by at least half. That's a huge deal. So what does that actually get us? Well, here's the beautiful result. You can only cut a number in half so many times before it gets down to 1, right? That number is logarithmic. This property guarantees that any path from any node up to the root can cross, at most, log n light edges. So any path in the whole tree is just a few heavy segments stitched together by a few light edges. Okay, so we've got these heavy paths, these chains, cool. But now for the really clever part. We're going to take this complex tree structure and flatten it into a simple, beautiful straight line, an array. We pull this off with a two-pass depth-first search. The first DFS is basically a scouting mission. We just go through the whole tree, count up the subtree sizes for every node, and figure out which child is the heavy one. Then, in a second DFS, we do the real work. We traverse the tree again, but this time, we prioritize going down heavy edges. As we do, we assign new positions to the nodes in a brand new array, making sure nodes on the same heavy path get consecutive spots. And here is the payoff for all that hard work. Every single heavy path in our tree now corresponds to a perfectly neat, contiguous block in our array. And once you have a problem on a contiguous array range, well, now you can unleash incredibly powerful tools like segment trees to answer queries on those ranges super fast. So we've done all this prep work, we've built our flattened array. How do we actually answer a query between two nodes? Let's call them U and V. The process feels kind of like climbing. We started our two nodes, U and V. We repeatedly look at whichever one is deeper in the tree. Let's say it's U. We'll query the part of its heavy path from U all the way up to the top of its chain. Then we jump across a light edge to the parent of that chain's head, and we do it again. We keep climbing chain by chain until both U and V finally land on the same heavy path. So why is this so efficient? Well, let's put the pieces together. We already know any path is broken into at most a logarithmic number of heavy path segments. And querying each of those segments in our array using something like a segment tree also takes logarithmic time. So that brings us to the final scorecard. You pay a one-time linear O of n cost to do the initial setup. After that, if you need to update a single node's value, it's a super fast O of log n. And the path queries, our main goal, clock in at a very respectable O log squared n. That's log n from the number of chains times log n for the query on each chain. Okay, this all sounds pretty cool in theory, right? But where do you actually see HLD pop up out in the wild? Honestly, it's a superstar in the world of competitive programming. It's the go-to solution for any problem that asks for aggregates, sum, max, min, over paths in a tree. But it's not just for simple stuff. It can handle more complex operations like XOR or GCD, and it works just fine whether the values are on the nodes or on the edges. Now, before you run off and start coding this up, just a quick word of warning. There are a few classic traps people fall into. A big one is getting the complexity wrong. It's log squared for path queries, not log n. Also, watch out for edge-based queries. They can be tricky and lead to off-by-one errors. And of course, remember the whole thing needs a rooted tree to even get started. It's also really useful to see where HLD fits in with other tree algorithms. It's in this perfect sweet spot. It blows simpler techniques like binary lifting out of the water for path queries. And while it's not quite as fast as the incredibly powerful and incredibly complex link-cut trees, HLD is so much easier to code and debug. For most static tree problems, it's the perfect balance of power and practicality. And that really is the big lesson here. Heavy light decomposition teaches us something beautiful about algorithms, that sometimes the best way to solve a problem on a complex, nested structure like a tree is to find a clever way to just flatten it, to turn it into a problem on a straight line where all of our best tools are ready and waiting. Makes you wonder, what other hard problems out there are just waiting for the right way to be flattened?